So here we are with exercise 6 in chapter 5. We are going to write code that implements standard matrix multiplication using for loops. And then we want to confirm using the matrix multiplication operator in NumPy, which is just the at symbol. Okay, this exercise will help you solidify your understanding of matrix multiplication. In practice, you don't want to do matrix multiplication in double for loops. Instead, you want to just use the at operator. Okay, pretty straightforward instructions, but I think this kind of exercise is really, really useful for helping you conceptualize and understand what matrix multiplication really involves. So here I generate two random matrices. It doesn't matter what numbers are in those matrices. And I'm specifying m and n to be 4 and 6. Now, you know that in order for this multiplication to be valid, the inner dimensions, so to speak, have to match. So the number of columns in the left matrix has to equal the number of rows in the right matrix. And then the outer dimensions, so m and m, will define the shape of the output matrix. Okay, so this is, initially it looks kind of similar to the code from a couple of exercises ago where we implemented matrix addition, adding two matrices together. But there we were looping over rows and then columns within one matrix. But here we are actually looping over m and m. So these actually correspond to the outer dimensions here. Okay, so then each element in the product matrix is not A times B. It is the dot product of this row in A and this column in B. So that means that the product matrix is not just the result of, taking one element from A and one element from B. It's actually a whole array of elements from A and a whole array of elements from B. Okay, so let's see. So that's matrix C1. And then here we have matrix C2. And we don't actually care what numerical values are in these matrices. We just care that they are equal to each other. Now, as I mentioned many times before in these videos and also throughout the book, we're not going to get, we are unlikely to get exact zeros when comparing these matrices because of tiny computer rounding errors and minor differences in implementation of what we are doing here versus the compiled matrix multiplication here. And this is going to be the more trustworthy operation, by the way. Okay, so instead, we're going to, I'm using this function is close. You have seen me use several different methods to look for approximate equality. Sometimes I just round to, let's say, 8 numbers after the decimal point. There's lots of ways you can do it. I like showing a variety of ways just to have a variety, give you different options. Okay, so run this code here and we get an entire matrix of true. And basically that means that these two matrices, C1 and C2, are extremely close to each other, which we can consider to be equal. And in fact, I think I'll do C1 minus C2 here. And this is the result that we expect to be 0. You can see some of these are exactly 0, some of these elements. Some of these elements are not exactly 0, but they're so tiny. The differences are so tiny, 16 orders of magnitude below any of the numbers that are in here, which is in the range of around order of magnitude 1. So when you are thinking about matrix multiplication in your head, when you're conceptualizing what matrix multiplication means, this is what I would like you to think about. This code is the image you have in your mind. But then in practice, when it comes down to actually implementing matrix multiplication in code, obviously this is way, way, way better.